Yeah, just for the logistics. So I'm going to share my screen to have some kind of virtual blackboard. Now I saw the duration is a bit non-standard. So how long do I talk and
we want you to talk slowly, and the talk is supposed to be 75 minutes, including the questions. So in 75,
right.
we want, because the local people wants to go to eat. Therefore,
exactly. So I know.
don't compete with lunch
with hunger. Exactly. Yeah. So I watched this thing. I think it's MIT. This How to Talk series, and it said the best time to talk is 11 a.m. But I think the worst time to stop talking is after 12. So anyway, so yeah, thanks a lot. I'll share my screen then and see how this works. Right. So what I'm hoping is that you see my screen and I mean my slide and nothing else from my computer. So I'm assuming that's the case. And right. So this is actually not really a normal talk, right? It's a job. It's a contract job, and I've been asked to prepare the ground for Bharatram Rangarajan, who will speak next time, and I should I plan to tell you a few things about vanishing results in bounds cohomology, and perhaps more importantly also why this has something to do with questions of stability that I know some of you have been interested in very much recently. And so here's my artificial blackboard. And I just want to point out here as a footnote that part of what I'm going to say is not very fresh fare, and so this older work has been obtained jointly with Marc Burger and Yehuda Shalom, and I'll try to put it perhaps in a slightly more current perspective and tie it in with the things I've been thinking since, and things that we've been thinking about together with Lev Glebsky, Alex Lobotsky, and Bharatram Rangarajan. So I'd like to start with the stability question of unitary representation in order to justify then going towards bounds cohomology. And I'll put some air under my laptop because it's already sweating. All right. So stability, and more precisely stability of unitary representations, and what I'd like to say here is as little as I can to get started. So let G be a group. And what we shall call an epsilon representation. So an epsilon representation or epsilon unitary representation is a map. It's not a representation, it's a map, but it looks like a representation. So it's a map pi from the group to a unitary group. And here n is either finite or infinite. So it's mapped to a unitary group such that the mistake we make when you compare pi of x, pi of y, and pi of xy is less than epsilon whenever x and y elements in the group. And so already at this point, I should say that this is not completely well defined because it depends, among other things, it depends on what exactly we mean by this norm. And this will be here just the operator norm or matrix norm, even if we're in the finite dimensions. So it will depend on that. And it will also depend on whether we're interested in the finite dimensional case or also the infinite dimensional case. But in any case, that's an epsilon representation. And the question that has been asked now for quite a while by, well, it's in some sense attributed to Ulam, but Ulam asked this very general stability question. And I think Kazhdan has been asked, David Kazhdan has been asked specifically by Vitaly Milman about this question. So the question is pi close to an actual representation, so to a true unitary representation? And here again, perhaps close is not very well defined, but I think we all understand what this means. This really means in the sense of calculus 1, namely, is it true that if you're an epsilon representation, you are delta close to a true representation? And in particular, is it true that, for every delta, there's an epsilon, such that epsilon presentations are delta close? And then you can ask a question more specifically, and you can drill down on the relationship between epsilon and delta. You could ask, is it true that every epsilon representation is, I don't know, 2 epsilon close to a true representation? And so on and so forth. And so before going further into that, I'd like to give a toy example, really a very silly example, but a silly example will illustrate not only that the answer to this question is in general no, but it will also illustrate that there's clearly some kind of connection with cohomological questions, and specifically with bounded cohomology. So here's the toy example, and I'll take a new blackboard for that. I can always come back. So the toy example comes from so-called quasimorphisms. And so a quasimorphism, is a map. It's a little bit like an epsilon representation, but to the additive group of reals, so not a unitary thing. So it's a map F from G to the real numbers, such that the mistake I make if I compare f of x plus f of y to f of xy is bounded. So it's the same definition, but to the additive group of real numbers. And so instead of being epsilon, we just say bounded. And so here's the toy example is that there's an easy exercise, namely exercise. If f is not at finite distance from a true homomorphism, then G is not stable. So does not, the answer to Ulam's question is no, is not stable, even for the one-dimensional case, even for U of 1. So that's a nice exercise. And the solution to the exercise, well, at least the hint is to consider the following epsilon one-dimensional epsilon representation. You just consider e to the I epsilon times f. And so if epsilon is very small, then the mistake, the multiplicative mistake, so the unitary mistake I make here is clearly e to the I, the additive mistake there. Since this additive mistake is finite, then when epsilon is small, the pi is really an epsilon representation. And then we have to think a little bit more why this epsilon representation cannot be close to an actual representation. So basically, the point is that if you want to switch from this multiplicative notation to the additive notation, the mistake you make in 2 pi z, and 2 pi z is, a mistake in 2 pi z is either big or 0. So a mistake in 2 pi z is at least 2 pi. And therefore, you check in that way that if this epsilon representation here is really delta close to a true representation and you can make delta go to 0, then in fact, this quasi-homomorphism F would be close to a true homomorphism. So this is a source of an instability of epsilon representations, provided, of course, that we have non-trivial examples of quasi-homomorphisms. And these are known since the 70s. So example of such a quasi-homomorphism. So example of F, you can take G to be the free group. And indeed, a similar construction works with surface groups. You can take G to be a free group. And you take F to be the counting of the occurrences of a word, such as, for instance, the word could be AB. Now, we know that the way to find homomorphisms for the free group is to count occurrences of a letter in the alphabet of the free group. And if we count the occurrence of a word, then we actually make a mistake. Because if I count the occurrences of the word, well, a short word like Alex, for instance, in a long sentence, then it could be that one sentence ends with al and the next one starts with X. So none of them contains the word Alex, but the concatenation contains once the word Alex. So we can make a mistake. This mistake is bounded because when I multiply two words, I have only 1 point of concatenation. And so it seems that the mistake I make is at most 1. And this is indeed true up to considerations of the sign, because we have to look at inverses of words and of letters and of sentences. So that's a fundamental source of instability. And here's a fact that has been proved by Marc Burger, Takao Ozawa, and Adhas Tom. Fact is that this can be induced. So the usual notion of inducing representations. So this can be induced. And therefore, if G contains a free subgroup, then G is not stable. The only caveat here is that when I induce a representation from a subgroup, in principle, even if I induce a representation to a one-dimensional Hilbert space, the induced Hilbert space will be infinite dimensional because it's some kind of function space on coset elements. So the caveat is that this conclusion holds for, in general, for U infinity. All right, but this already tells us we've already covered a little bit of grounds because groups containing free groups fail this stability question. Now,
can you remind me what stable means?
Right, I didn't say it explicitly. I apologize for that. So stable means that the answer to this stability question is no. Namely, stable means that you can find an epsilon representation that is not close to a true representation. And to put quantifiers in that, you are unstable if you can find a sequence of epsilon representation with epsilon going to 0, but remaining at positive distance, at bounded below distance of any true representation. So let me
you're using the Hilbert's the operator norm in this.
Yeah. So this is all in the operator norm, and these kind of questions change considerably when you change from one norm to another. Yeah. Now,
by the way, since this is an arithmetic group seminar also, the Rademacher function on conjugacy classes, SL2Z doesn't have homology, the rank is 0, but there is a quasimorphism, which is a nice arithmetic function coming from the Dedekind eta function, by the way.
Absolutely, and I think there's a beautiful paper by, I believe it's Jean Barge and Etienne Gis, who show that in fact this same function can be realized in many equivalent ways, and one
the linking of a closed curve around the trefoil when you realize PSL to R over PSL to Z. Yeah, it's beautiful.
Yeah. Or even so for somebody less arithmetic, and I know this is an arithmetic seminar, for somebody less arithmetic, you would say, well, all this lives in SL2R, and basically this is just the obstruction from extending the homomorphism from S1, the maximum compact subgroup of SL2R. The identity homomorphism to itself doesn't extend to SL2R, but the obstruction to extending it is exactly this quasi-homomorphism. So now I'd like to say something in the opposite direction, and I hope this will bring us immediately closer to cohomological consideration. So to go in the opposite direction, I'll quote a beautiful result of David Kazhdan. So we now go in the opposite direction. So opposite direction, meaning towards stability. Here's a theorem of Kazhdan. So the short way to state this theorem is to say amenable groups are stable. And I'll give a longer statement also. So I'm not completely certain that in our arithmetic seminar we can take for granted the definition of amenable. So the definition is G is amenable if there exist an invariant states on the space of all bounded functions on G, which we can take continuous if G is locally compact instead of abstract. I don't want to distinguish now. So it's a generalization of finiteness. It means basically you can average bounded functions on G, or you can count, you can assign a mass to any subset of G in an invariant way. And examples includes all compact groups, soluble groups. So in the context of arithmetic lattices, we can think of minimal parabolic subgroup of the ambient Lie group. Now the way that's
if there exists an invariant
state, he's talking
states.
Like...
So a state is a finitely additive measure, or I say state because I'm in the linearist case. So this is a positive unital functional linear form. So positive normalized linear form. Yeah, so it's like a probability measure on G, except it's only finitely additive and defined on any subsets. And so just by fixed points theorem, for instance, Markov-Kakutani tells us that abelian groups have this property. And
a finitely additive measure defines positive on measure on what kind of sets? Repeat, because they can be subtle.
Any subset. For abstract groups, and if we're talking about locally compact groups,
you're not putting a topology. You're not putting a topology on G.
So you can give a definition in the abstract case or in the topological case. In the abstract case, it's easier because you.
Topological case.
Okay, so in the topological case, then my advice is to only consider locally compact groups because that's much simpler, and then you can take an invariant mean equivalently on. So in the locally compact case,
Reynolds sets or on the vague measurable sets. That's all.
Either is fine.
Okay.
Either is fine. So you can work with L infinity, and it's also enough to work with continuous bounded functions. But this equivalence is slightly subtle and fails completely for non-locally compact groups, which is why I don't like. There's a universal definition that works for any topological group in the world. It is to say, and that's my favorite definition, it's much simpler, is to say that the group is amenable if and only if it has a fixed point whenever it acts on any convex compact set in any locally convex topological vector space. And so this definition, referring to continuous actions, works for any group, topological, locally compact or otherwise. So the important example is so soluble groups. And in the locally compact setting, compact groups are also examples, and therefore we get any minimal parabolic in any semi-simple Lie group or algebraic group. Now, what Kazhdan really proves is a statement that might sound perhaps a bit technical, but I think really illustrates that there's something cohomological perhaps going on, namely. Kazhdan proves that pi epsilon representation can be replaced by another pi prime epsilon representation that would actually be better. So I'm not sure I have the exact numbers here in front of me. I don't, so I'm going to go out on a limb and say that it's epsilon over 2 plus 5 epsilon.
Sorry, just to be clear, you're always going to be talking about operator norm into a Hilbert unitary. Always. Okay.
Always, yeah. In this lecture, always, and actually, I'm going to soon stop talking about it altogether because I want to talk about cohomology. So, yeah. So Kazhdan shows that you can find a representation with a smaller epsilon, something like epsilon over 2 plus 5 epsilon squared representation at distance, let's say less than, again, something like epsilon over 2. I'm going to be safe of pi. So what Kazhdan is really proving is that you can take pi and make it better. This is much better because epsilon squared is much smaller than epsilon. You can make it better without going too far. And so if you repeat this infinitely often, which is what Kazhdan does, then you end up making it a true representation. This goes to 0, but you don't move infinitely far because this ends up being bounded by a geometric series since we divide by 2 and add a little small mistake. And so going at a distance that is of the order of epsilon, you replace pi successively by a true representation. And the way he achieves that is really by applying the definition of amenable groups and by averaging something. Now, the thing that's going to be averaged is not quite a number, So it's not going to be a number, it's going to be vector valued averaging, which is fine. And the object that we want to average is the mistake that the almost representation makes. So the idea of the proof, I cannot spell this, average over G, so over, let's say, little g and big G, the following object, you take pi of x star. So this is morally we take the inverse of pi of x. We actually do take the inverse of pi of x since it is unitary, and times pi of xg. So this is essentially the mistake that G causes to any other group element. So we average over, and I'm sorry, we average this over X and G. We average over X and G, and this will give us pi prime of G. So this average of this mistake is how Kazhdan defines pi prime of G. And so I prefer to write here a star rather than an inverse, because I want to see in what subspace of the operators I am to be able to perform this averaging. Anyway, that's just the bare bones idea, but it kind of makes sense that if I take the mistake of my representation and average it, I should improve this mistake. Now, here's a nice exercise. If you take this idea and apply it to the toy case of the real values, the scalar valued quasi-homomorphisms, then averaging something additive works very well. And so the exercise is to check that if you apply this to a quasi-homomorphism with real values, you find on the nose a true homomorphism. So this gives you really a one-line proof that amenable groups don't have non-trivial quasi-homomorphism, because you take your quasi-homomorphism, you average it, everything is then additive, you have a minus here, everything is additive, and you have corrected this to a true homomorphism simply because the averaging was G invariant. If you do this in a non-commutative target here, this will not quite work, but Kazhdan's remarkable observation or remarkable proof is that even though it doesn't work, it makes things better. And so it makes things better by quantifiable amounts, and so ultimately it solves the problem. So that's Kazhdan's proof for amenable groups.
Is this a kind of gauge principle that like depends on, like, I mean, why is it specific for the, because of the topology of the unitary group, you can do this?
I don't think it's really the topology. So one thing that makes this work is definitely the fact that we take the operator norm, and in particular that we work in a dual space. The space of all boundary operators is duals. There are many other norms that also are dual space, so it will also work for these other norms. And Kazhdan actually states and proves it in this wider generality. I'd like to jump immediately to the problem that I'd like to talk about, and I don't know if it should be called a conjecture or an almost theorem or whatever, but this I leave to Bharat to talk about this. So well, I'm just going to write conjecture, and maybe at Bharat's talks it will change status. So any higher rank lattice is stable for the finite dimensional unitary representations. It can't be for the infinite dimensional ones since they contain free subgroups, but we would like to say that they behave like amenable groups for the finite dimensional case. And in order to approach this, I need to talk to you about bound cohomology. In fact, that's my only job today, is to talk about bound cohomology and the relation with that. So first, I'd like to put below this statement a theorem. And well, no, I'll first give you some definitions. Okay, so
suppose I haven't thought about bounded cohomology, and I'm just looking at this in U1, where there are no characters for higher rank. So is this some kind of rigidity feature? This is a very strong rigidity statement, I guess, of sorts.
Right. Right. I think that's the idea. Is that it's saying that not only this lattice have all the rigidities that we know and love for representations, for homomorphisms, but that it should even survive for almost homomorphisms, at least in this context of want to make it precise.
Right, because if you could deform it would be, so stability, rigidity is sort of needed, but this is much stronger stuff.
Right. And actually I should say that even the baby case, the toy case with the quasi-homomorphism and the one-dimensional unitary representations, it is true, but not absolutely completely transparent that you can invert this stupid construction of exponential and somehow with a logarithm that you can say that the stability in U1 is the same as not having quasi-homomorphisms. So something like that is true, but it would require, so it has to be stated a bit more carefully, and I don't want to get into that because we really care about the stronger statements about the n-dimensional, not the one-dimensional stability. So I need to give at least a short definition of what bounded cohomology is, and then I can explain why it is connected, and then I would like to say a few words about vanishing. So here's a definition that is in a sense due to Gromov, 1980.
I should tell you a story. First time I met Gromov, I said, your bounded cohomology suggests something. He said, transcendental nonsense.
He said, I didn't catch this. He said what?
He said that it's transcendental, and he invented it. But then when I was asking him about some question about, he had various problems that would follow from it, but he said you can't compute anything.
That's the main problem with bounded cohomology, and actually until not so long ago it was I think a true statement that the only things that were known about bounded cohomology is that it was vanishing in some cases and pathologically huge in other cases, and now finally we know that, for instance, we know a few groups where we can really compute it completely, like for instance Thomson's circle groups or such things, but it's a nightmare to compute. That's true. Luckily, we don't need to know so much about it to try to apply it for stability. We only need to know what happens in degree 2, and we only need to try to prove vanishing in degree 2, and that's what I'd like to present today. So the short definition of bounded cohomology is that bounded cohomology, that will be denoted like cohomology but with a little b for bounded, is the cohomology computed using bounded cocycles and, very importantly, bounded coboundaries. Because cohomology is a quotient, and so it really makes a big difference if you quotient by something smaller. So that's an informal definition, but it can easily be turned into the official definition. And so more generally, I'll say more, but more generally, you can do this with non-trivial coefficients, where V is a Banach module. So Banach space is a representation. So that's a concrete definition. That's definition where you can write down your space, but you can't compute it. And it turns out the reason why I also credit Johnson 10 years earlier is that this is exactly the same thing as the completely usual cohomology of, not of G, the completely usual cohomology of the Banach algebra L1 of G, the convolution algebra. And that has been introduced and studied by Johnson in 1972. And it's not surprising that it's the same thing, because linear forms on the convolution algebra are exactly bounded functions on the group. So it's exactly the same thing. Now, I'd like to state two facts that seem very plausible or maybe even obviously true for this bounded cohomology, and hopefully tell us why it's relevant to stability.
There's a lot of functional analysis here that is vague in my mind. So L1G, if you look at it as a Banach algebra, its maximal ideal space, is that understood for these kind of G? I mean, is that related to this cohomology theory of L1? What is L1 of such?
Right. So L1 of an algebra. So this is a side comment. If A is an algebra, and more generally a topological algebra like Banach algebra, the cohomology consists in looking at multilinear forms. So because what is homology? homology consists in looking at A tensor A and so on. We go in the opposite direction. So homology consists in, well, you can define it with derived functors too, but the derived functors will be computed using the using tensor products, and so the cohomology will look at multilinear forms because the dual of tensor product is multilinear forms. So what is relevant is linear forms on L1 of G and multilinear forms on L1 of G, and the dual of L1 of G. So the space of linear forms on L1 is exactly L infinity, the bounded functions. Multilinear forms on L1 can be identified with bounded functions on several copies of L infinity. So you will really compute, if you look at the dual, you will get a standard resolution for the bounds cohomology of the group, and the standard resolution will consist in looking at multilinear functions on G. And since the functor that we try to derive in cohomology, generally speaking, is the functor of G invariance, we look at G invariance multivariate functions. So if I did this without pronouncing the word bounded ever, I'll just be giving you the 10-second definition of ordinary group cohomology, and this would be the bar resolution to compute group cohomology. And when you compute bounded cohomology, the only thing you do is you add the word bounded everywhere. And it turns out that, unfortunately, this makes everything very hard to compute because many of the standards techniques are not compatible with adding the word bounded everywhere. But instead of telling you what goes badly, I'd like to tell you what goes well. And I think I can convince you of two facts that are plausible, and that these two facts really tell you why it's relevant to stability and to Kazhdan's theorem. So the first fact is, I go back to white. So fact one. So we have a forgetful map that forgets that something is bounded. So I can go from the bounded cohomology to the ordinary cohomology, just forgets the word bounded in the definition. This forgetful map, even though I take a bounded cocycle and I forget that it is bounded, it is not at all an inclusion, because then I also have to forget that the coboundaries are bounded. So I have to forget that everything is up to bounded functions, now up to functions. So it can have a kernel. And the kernel corresponds to almost cocycles in degree 1 less. Why is that? Because what does it mean that I'm in a kernel of such a forgetful map? It means that I consider a bounded cocycle, and this bounded cocycle is actually trivial if I allow unbounded maps. So if I turn it around, it means I have an unbounded map whose coboundary is bounded. So I have an unbounded map that is not quite a cocycle, but if I compute its coboundary, I find a mistake, and this mistake is bounded. So that is exactly what we do when we look at.
You emphasize that in bounded, there's both the co-kernel and the kernel where you're going to have this difficulty when you have to put bounded. And it seems like
I'm sorry, I couldn't hear that. I'm sorry, the connection is not great.
I'm saying that when you, as you pointed out, when you define cohomology, there's the kernel and the co-kernel where you're going to have to start. You have difficulties on both sides.
Absolutely, absolutely.
And it seems in this statement there's only one.
Absolutely.
And why is that?
Well, so there are two ways to answer. One way to answer is that it's literally when you try to identify what a kernel is, you find the definition of a cocycle up to something bounded. So it's not enlightening. But I could also say that basically there's the work on bound cohomology really splits almost into two halves that are essentially independent, which is you can study ordinary cohomology because you really don't give a damn about bounded cohomology. So you can study ordinary cohomology, but be interested in the numerical invariance associated with that. So characteristic numbers, for instance, and that will correspond to asking whether your ordinary cohomology is in this image, and if so, measuring it. Or you could ask, you can really study the kernel, and this consists in studying things that become trivial in cohomology, meaning that you are making a bounded mistake only. Let me write down an example. So example, if F is a quasimorphism, this gives a 2 bounded cocycle. So this gives something in H2 bounded of G, and more precisely in the kernel of this forgetful map. How? Simply by considering the map that to xy associates f of x plus f of y minus f of xy. So the mistake of being a cocycle, being bounded, gives you, well, this mistake is in turn a bounded cocycle. It's actually even a coboundary. It's trivial here because it's defined as the error of the cocycle equation. So the cocycle equation is the homomorphism equation, and its error will be this term here. And so we see that to say that the group admits quasimorphism not at finite distance of a homomorphism, the thing that interested us for the U1 stability, is exactly the same as saying that this forgetful map from bounded cohomology to cohomology does not have a kernel. So there it's really an if and only if, and it's very clean. Now the difficulty is that in Kazhdan's case, we are not commutative in the targets. And so it's not quite, first of all, you cannot write this additively. It's going to be something multiplicative. And it's not quite true that it's going to be, that the error is an actual bounded cocycle. And it's not even clear what the coefficient module would be. So everything is sort of ill-defined. And in Kazhdan's paper, he talks about epsilon cohomology, and he writes down the same thing and observes that everything is true up to epsilon, but it's not really a cohomology theory. And actually what we've been trying to do is Bharat, Lev Glebsky, and Alex Blotsky is to try to turn this into an actual cohomological theory. And that's what I'm not allowed to talk about. So I'm going to talk about the bounded cohomology, which is supposed to approach this question. And then later you will hear about the framework that turns this into a more appropriate cohomology theory. But still, this first fact shows us that there's clearly a connection between almost cocycles, in particular in degree 1 epsilon representations, and bounded cohomology. There's a second fact, which is also very plausible and very, actually, I would say, easy to check. And that is what happens with amenable groups. So fact 2, if G is amenable, then the bounded cohomology of G is trivial, actually in any degree, any positive degree. And even for non-trivial coefficients, so same for, which is relevant since we look at representations into complicated spaces. So same for non-trivial coefficients, and that is for any Banach module as long as V is dual, because it's in dual spaces that we really know how to proceed pointwise. So dual spaces are somehow function spaces. So this is not very hard to believe, that bound cohomology is completely trivial for amenable groups, because you certainly agree that ordinary cohomology will be trivial for finite groups, at least if you're with values in a field or in a vector space, because of a finite group, you can just average everything and average out any cohomological obstruction. Now, amenable groups are precisely the groups where you're allowed to average anything as long as it's bounded. And so from the viewpoint of bounded objects, amenable groups are exactly finite groups. So the proof that finite groups have no obstruction for any cohomological problem in any field or vector space, the exact same proof gives you that amenable groups are completely trivial from the viewpoint of bounded cohomology. So now the question is, we care about arithmetic groups in this seminar, and arithmetic groups are of course far from amenable, and we'd like to prove that somehow they have a vanishing of bounded cohomology, and I'd even like to give you an idea of how to prove that. So that's my mission now. So we cannot apply, I mean, these higher rank lattices are not amenable, however, they should have some vanishing results. So I'll first state the results, and then I'll try to outline how it is proved, and I'll try to convince you that at least on the level of the strategy of proof, the strategy can be made extremely simple and transparent, and hopefully even a little bit geometrical. I will try to convince you that there's something to do with the topology of the Tits boundary at infinity, the Tits building, associated to higher rank groups. And the states building is has a non-trivial geometry or topology precisely when the group is higher rank, because otherwise it's just a bunch of points.
Yeah. In the case, say, of SPN1, the lattice in SPN1 where you have super rigidity, that is not a case. Your methods are really genuinely higher rank, right?
Not only the methods, but the statements. So if you take a lattice in SPN1, it turns out that it admits also quasi-homomorphisms. So it's not even stable for one-dimensional representations. So yeah,
that's interesting. Even the
all of them. So
no, this is Peter. This is really usually we say that the dichotomy is between rank 1 and higher rank, and we correct it. Okay, but blah blah blah. This case, it looks like it's exactly dichotomy between rank.
Okay, so what's your position?
The rank 1 lattices, neither the uniform nor the non-uniform, are never stable.
Right, because so
I mean, you, I guess. So is that obvious? I mean, I know it for SL2Z, and you pointed out.
Right. It's so I can give you a plausibility argument, which I think is quite believable. So the business that we did for the free group, counting words. So there I want to be more geometric than the independent eta function. Counting words in the free group is something that you can imitate for any hyperbolic group, because instead of looking at words and thinking of them as paths in a tree, you think of them as paths in a gamma of hyperbolic metric space. So if you're in strictly negative curvature, you can do that, right? So this takes care of uniform lattices, and non-uniform lattices also do that. Right. All right. So a statement of vanishing for higher rank lattices. So here's a theorem that we proved a while ago with Marc Burger, and that is that for higher rank lattices, by which I mean an irreducible lattice in a semi-simple Lie group, or more generally in a product of semi-simple Lie groups and simple algebraic groups over varying local fields of any characteristics. So generally the general case of higher rank lattices. So for higher rank lattices, we have vanishing of the second bounded cohomology. And the second one is the important one, because this will measure the defect of a one-dimensional thing. So it's the mistake of being a homomorphism, for instance. So this will vanish for large class of coefficients. So I would say for most V, and I can tell you exactly which ones. So it's always true if V is a separable dual. I don't think we proved it in that generality back then, but it's always true if V is separable dual. At least if you assume that it has no trivial parts, no invariant vectors. So this is a circumstance on which I don't want to insist, because even without this assumption, it is still true that the kernel of the comparison map vanishes, and that's what we care about for in the discussion. So, but otherwise we have to worry about groups of Hermitian type. But so except this detail, which is really, I mean, today it's a detail, maybe next week it's going to be less of a detail, but today it's a detail because it doesn't concern the kernel. We can really prove vanishing for any high rank lattice for a very broad range of coefficients. And in fact, this theorem, luckily I don't need to try to tell you how to prove this theorem, because it follows from another one, and that's the one I want to focus on. So it follows from the theorem we really proved is that same for the ambient semi-simple group. So exactly the same statements, that H2 bounded of the ambient Lie group or ambient semi-simple group vanishes, and provided again that there are no invariant vectors. Okay. So the fact that this second theorem implies the first is really not surprising, because once again, the idea is that if you want to prove something for gamma, then all you have to do is you have to induce the representation of gamma to a representation of G, so it will change V. And so this also is the reason why it's really important for us to deal with general coefficient modules and not just with the real numbers. Even if you care about only one-dimensional stability, for gamma, it will be infinite. Well, it will be some infinite dimensional module for G because it will be the induced module. So the proof of this implication is really induction, and it comes, of course, with technicalities, but it holds. Induction, so the so-called Ekman-Shapiro lemma. And so what I'd like to discuss is what is the strategy to prove this theorem here, and why it has something to do with Tits building. So again, what are we trying to prove? We have a semi-simple Lie group or algebraic group of higher rank, of rank at least 2. We have some Banach space with a representation and no invariant vectors. So this will be used. And it is a separable dual, but you can think, for instance, of all operators of a finite dimensional Hilbert space. That would be a good example. And then what we try to prove is that the bounds cohomology in degree 2, which is supposed to have something to do with the mistake that you try to do when you have a homomorphism, is trivial. So that morally, you should hope at least that if the mistake of a one-dimensional, of a homomorphism, that it should be possible to perhaps not kill this mistake, but to make it smaller the same way Kazhdan made it smaller. And that will then be the starting point of our joint work with Alex, Lev, and Bharatram. Right, so in the remaining time, I'd like to give an idea how to prove that. And there are 2 main ingredients. One is the idea of the Tits building, but I'll try to bring it down to something very, very concrete and explicit. And 2, a notion of ergodicity. These are the 2 needed ideas. And I'll start with the notion of ergodicity, starting by just recalling what ergodicity means, because I want to generalize it. So if a group G acts on some measure space omega, we say that it is ergodic if any invariance map, measurable map from omega to R is constant. That's one of the definitions of ergodicity. And the reason I want to recall it is that in this definition, there's no harm if you replace the real numbers by any separable Banach space. It really doesn't matter because the only thing that counts is that this is some kind of Polish space, right? So it changes absolutely nothing. But I would like to do that because now I'm going to define a much stronger condition than ergodicity that we'd like to call ergodicity with coefficients. So an action on measure space is ergodic with coefficients if the same holds.
You're not assuming that omega's got finite measure either, right?
I don't think it really matters because you only ask if a measurable map is essentially constant or not.
Your definition doesn't assume it. Right.
No, but you could add it to the definition. It wouldn't change anything because you can replace the measure by a finite measure in the same measure class. So I suppose I'm assuming that it's a standard measure space, that it's a sigma finite measure space.
I'm just trying to understand whether should we be thinking of it being finite measure, the whole.
It doesn't. I don't think you should, but you may.
All right.
You may, but it won't change anything because again, since I don't actually measure anything, I just look at whether measurable maps are constant or not.
And the only reason I'm saying it is because I don't know where I look there. I should look there. Where should I look? I don't know.
Okay, yeah. So we will apply this definition to G mod P. So we'll apply it actually to a finite measure space, but with a measure that is not invariant. Okay, so we'll apply it.
it's just you're giving a definition, and most people, for me, the definition of ergodic means it's either measure 0 or 1, but it's a minor point. Forget it.
But it doesn't have. Now I understand.
Really,
Okay.
it's irrelevant.
Now I understand your question. So for me, the definition of ergodic is not 0 or 1. It is either measure 0 or the complement is measure 0.
Yeah. Okay. Got
so
it.
yeah. Okay. So now ergodicity with coefficients, you require the same, but for many more maps, not just for invariance map, but for all equivariance maps to all separable Banach modules. So this seems to be almost impossibly strong because you can imagine that if omega, for instance, is the group itself, is G itself, then it will never be ergodic with coefficients, because you could map a point G to just the orbit on the G of a given vector, and that's not constant if you allow non-trivial representation. So it's a much stronger definition. But the point is that there exist such spaces, and in fact, here's a very nice fact that is, I think, in this seminar perhaps an exercise even. So if you take G semi-simple, and P minimal parabolic, or actually any parabolic, then the action of G on G mod P is ergodic with coefficients. In fact, even more is true, even the diagonal action on the square is ergodic with coefficients. And what is the proof of this fact? The proof is any point in G mod P or even in G mod P squared has an unbounded stabilizer. So points have unbounded stabilizers, namely, it's the stabilizer of a pair is just the intersection of two conjugates of P. So let's say P1 intersection P2. And we know by Mountner's phenomenon, or we can think of it as a version of Howey-Moore, that if I take something that is invariant under any unbounded subgroup, it's actually invariant under all of G, and then I go back to ordinary ergodicity. So it means that the action of a group on G mod P and G mod P square even is so much better than just ergodic, right? It has an ergodicity property that fails completely for dissipative actions, such as the group acting on itself. So that's the first ingredient. And now let's see how to use this. So I'm now simply going to outline the proof of the theorem and see what we need and see at what point we'll need higher rank and why this reflects on the structure of the Tits building. So here's the strategy of proof. So the proof of the theorem, at least on the strategy level. Right, so we want to show that the second bound cohomology of G is trivial if V has no invariant vectors. That's what we want to prove. So this is to show. So what is an element of the second bound cohomology? So we agreed that it can be represented as a bounded cocycle. So more precisely, omega here is a map of 3 variables on G to V that is G equivariance. Because when you take this equivariance models, we have one more variable, so this is the bar resolution. So the first step is that since we talk about bounded cocycles, we agreed that we can average anything amenable. We can average out everything amenable because bounded functions can be averaged over amenable subgroups. So without loss of generality, omega goes in fact from G mod P cubed to V. Right? P is amenable, P is the minimal parabolic. And we discussed at the beginning of this talk that these guys are amenable. All right, so we can assume that. And now the next thing that I'm going to say is I'm going to take some more parabolic subgroups. And so if I'm of higher rank, I know that I can take more than just a minimal parabolic subgroup. So let's Q be a parabolic subgroup. So let's Q be any parabolic, in fact. Now we consider not anymore the bounded cohomology of G, but of Q. And if I take a parabolic subgroup, it has a radical. So let R be the radical of Q. Okay. R is amenable, so I can also average it out. So it means that the bounded cohomology of Q is the same as Q mod R, and therefore, having averaged it out R, I also land in R fixed points in my module, right? So what I'm doing is I consider the subgroup Q parabolic, and I want to look at the cohomology only of this subgroup. And I observe that it has an amenable radical, and anything amenable I can always cancel out, as we did here already, but now it's a normal subgroup. So I really mod it out here, and it means that I land in R fixed vectors because I've killed R. So now my invariance maps must be R invariance. However, once again, we want to remember the mountain phenomenon or the Haumur phenomenon. That's the same as G invariance things, which in our assumption are trivial. So what I've observed here is that if I start with the cohomology of G and I just restrict it to any parabolic, it will vanish. So perhaps that's not great, but it's a start. So each time I go to parabolic, it vanishes. If I did that for the minimal parabolic, it would not be very instructive because the minimal parabolic is amenable. But in higher rank, I can pass two parabolics that are not amenable. So this observation, simple as it is, has a potential for progress. So let's see what we can do with that. And the idea will now be to vary the parabolic that I consider. And if I said that I want to use the structure of the Tits building at infinity, that's perhaps pedantic, but I mean, after all, the Tits building is by definition the collection of all parabolics.
Nicola, this was
it's time to finish.
A bit too fast for me, even though I already seen it several times. So please do it a little bit slowly. So once you take Q, and we are at the point where H2 BQR over VR now is 0 because this is equal to V2, and therefore this is 0. Maybe you can just write everything. Yeah, now try to write everything. Okay, now again.
And from now on, I write everything, right? So the conclusion of this discussion is that the map, so hence, we care about the bound cohomology of G. And what I observe is that if I now restrict it to any parabolic Q, this map will be 0. So my cocycle will be 0 for any parabolic. And now I'm going to apply this principle to two different parabolics. So I change slide and I choose two parabolics. And I tell the hungry people that the proof is almost over. So let's Q1, Q2 be two parabolics. Okay, so I had my cocycle with 3 variables. I want to write it again here. And I know that it becomes trivial for each of these parabolics, for both QIs. Now, what does it mean to be trivial? It doesn't mean that it's all of a sudden 0, right? It means it's trivial in cohomology. So what this means is that it's a coboundary. So omega is of the type boundary of some other map, beta I, where now beta I has one less variable. So it's a function now of 2 variables. And to say that it's trivial for QI means this function of 2 variables is not a cochain or an object for G, it's only an object for QI. So it means that this is only QI equivariance. Now, the reason I do this for 2 parabolics is that I want to is that for each parabolic, I argued that I have a way to trivialize my cocycle for the viewpoint of each parabolic. And what I want to do next is I want to compare these trivializations for 2 different parabolics. So I compare beta 1 and beta 2, and I ask, what is the difference? So beta 1 minus beta 2 is a 1 cocycle. It is degree 1 less than omega. Why is the 1 cocycle? Because the boundary of beta 1 is the same as the boundary of beta 2, right? In both cases, it's omega. So the boundary of beta 1 minus beta 2 is omega minus omega is 0. It's a 1 cocycle, but for which group? Since beta 1 is for Q1, beta 2 for Q2, this is only equivariance for the intersection. Yeah.
Just a second. Why beta 1 minus beta 2 is 1 cocycle?
Because if I ask what is the coboundary of beta 1, it's omega. What's the coboundary of beta 2? It's also omega. So the boundary of the difference is omega minus omega, which is 0.
Okay.
Right?
Yeah, sure.
So it now becomes a cocycle in degree 1 less. So if you think of, for those who notice buildings, I'm somehow doing an induction on the dimension of the face of a face of this building. So it's now 1 cocycle. So for which group? For Q1 intersection Q2. Okay, so now there are 2 ways to think about it. We could think that Q1 section Q2 could be, for instance, a minimal parabolic, in which case it would be amenable, and I could say this is a trivial thing. But I could also argue more generally and say that H1 bounded.
What you could argue that they contain a minimal parabolic because of the higher.
Sorry, I regret what I said. Let me not say it and say something simpler instead. So let me say that H1 bounded is anyway always 0, because this is just a form of the Ril-Narjewski fixed point theorem. It's a form of it. Now, can I spell this? Narjewski. Because basically, we never talk about one bounded cohomology, because what is a bounded homomorphism? It's right. So, or a bounded crossed homomorphism to a Banach space. It's really an action with bounded orbits, and for the type of modulus we have here, they always have fixed points by various instances or variations of the Ril-Narjewski fixed points theorem. So there's never H1 at all. We're already at the bottom of our induction. What is this theorem? I've never heard of it. Okay, take a separable dual Banach space. Any affine action with bounded orbit has a fixed points. Any bounded? And so, can you write Okay. So V separable dual, and think of the baby case Hilberts, then it's okay. And if G acts on V affinely with bounded orbits, then there exists a G fixed points in V. And now we have to remember that affine actions is exactly H1, and fixed points is triviality of H1, and bounded orbits is saying that we look at bounded H1. And so this statement here actually implies, or is really equivalent to saying that H1 bounded of G, any group G, it doesn't matter, is always 0. Okay, thanks. Yeah. So you can apply that to the intersection, to the minimal, to the intersection. Absolutely. Well, the problem is I took back the idea of the minimal one because in a very high rank, I will very soon want to take Q1 and Q2 to be maximal parabolics. Right. And so maybe the intersection is not as small as I was hoping for, but I could also have used again the same trick of the radical of this group. Actually, I could also have used the trick of the radical of this group to kill. Yeah, so there are multiple ways, but I guess the cheapest way is to say that there's a statement that holds for any group in the world. So at this point, I know that this difference here is again trivial in cohomology. So what this means, as here I have to write down what it explicitly means. It means that in fact, beta 1 minus beta 2 is the boundary of something else. Now alpha has only one variable left, but also it's only equivariance for Q1 in section Q2. So, right. So, and now we're really almost done. I see the time is running, but we're really almost done because now I have a map of one variable on G mod P that is equivariant under something that again contains P. This contains P again. And so I meet the ergodicity risk coefficients, because a map, so to be P equivariance on G mod P is the same as being G equivariance on G mod P squared. And therefore, this map alpha is constant. So the map alpha is constant. Now we just need to go back and to see that we solved our problem. Alpha was, the boundary of alpha is now 0 because alpha is constant, and that was the difference between beta 1 and beta 2. So alpha constant means d alpha 0, but that was beta 1 minus beta 2. So I proved that beta 1 is actually equal to beta 2, but omega, I trivialized it using either beta 1 or beta 2. Okay, so now I have this, but for beta I, Q1 and Q2 equivariance. And now it remains only to say that I can always take two parabolics, which together will generate the entire group. So these two together generates G. So beta I is G, is a G cocycle. And since beta is trivializing omega, I proved that omega is trivial even for G. So perhaps it was a bit fast in the end, but that's really the end of the proof, and I'm happy to go back to anything that I've left unclear. In particular, I'd like to really emphasize where higher rank is used here. So higher rank is used in saying that I can take two parabolics which together will generate the entire group.
Yeah, this kind of it's a flag argument that's already, I think, appears in Selberg's local rigidity. We first proved it for SL3, and then Mostar rigidity in higher rank. You make similar kind of playing with the intersections of parabolics, wouldn't you say?
So I think I have to trust in that, because actually I came to this from exactly the opposite end. So the place I came from was actually to show that what I proved some years later was that you have this vanishing for all n below the rank. And so for me, this is an analog of the theorems of Borel and Serre, where they prove the vanishing below the rank of all, or Borel and Wallach also below the rank for all semi-simple groups, in order to prove that the lattices actually have the same cohomology as the ambient group below the rank. And the way they prove it is by using a Solomon-Tits theorem that says that the Tits building is contractible in dimensions less than the rank. I mean, it's somewhat equivalent to a bouquet of spheres. And so this argument that I sketched here in a very down-to-earth way really tells us that in the measurable sense, the Tits building is contractible up to degree below the rank. And that's really what I prove, is that there's measurable homotopy of the Tits building, and this gives the vanishing below the rank of all these cohomologies. So I did not think of it in degree 2, really. I thought about
just distinguishing rank 1 and higher rank in terms of rigidity properties. But those are rigidities of deformations of gamma. And what about higher n on H2?
Right. So exactly. So you can go below the rank, and in fact, it turns out you can even go below twice the rank. So exactly the same statement is true, that this is 0 if you're below twice the rank, and as long as the coefficient module has no invariant vectors. So. And
then, I mean, and bigger n?
You mean higher than the rank?
Yeah. Is that obvious?
It's nothing is known. So really for these familiar groups, we really don't know bounded cohomology above rank. And actually, I have to say, even if I remove this assumption, if I look at trivial coefficients, then conjecturally we should find the same as the usual cohomology of the Lie group. But this has been conjectured already by Dupont at the end of the 70s, and is completely out of reach at this time.
But let me ask you a technical question, because maybe in Borel's work where he has to go from L2, so you have a gamma as a lattice, right?
Yeah.
You want to relate the group cohomology to the L2 cohomology, and the L2 cohomology you can compute using, you've got vanishing theorems and things like that. So you have to work quite hard with the kernel and the co-kernel. Are these things, you have a new viewpoint on that?
I love the question, because there's actually a similar difficulty. I mean, especially if the lattice is not uniform. But I'm not sure it's exactly what you have in mind. But one difficulty that you have is that if you do this induction to go from gamma to G, since we're talking about bounded cocycles, we just like Borel had the problem to justify that he remains in that you can guarantee some L2 condition, and you need to know something about the fundamental domains and reduction theory and so on. Here we have an even bigger problem, which is actually becomes a very big problem, which is that you have to deal with bounded functions on G mod gamma essentially. And unfortunately, since we talk about bound cohomology, unfortunately this beast is much less nice, well behaved as L2 spaces. And in particular, it's not a separable dual, it's not separable at all. And
I was thinking that maybe you're much more, so this looks much harder, the functional analysis much more difficult, that maybe you have a new treatment of the difficulties here, which are softer or not. He worked quite hard. I mean, he spent a lot of effort fixing this up.
Yeah, no, I mean, to be fair, some things are harder, but some things are easier. So in fact, here there's something that is maybe easier, namely that indeed you end up in this ugly space, but this ugly space has one nice property, which is that you can consider it as a subspace of L2. And so this looks like a very bad idea because it's not closed, it's not the same norm and so on. But it's just good enough to try to apply this ergodicity that I mentioned for separable coefficients within L2 and then bring the conclusion back to L infinity. So in that sense, some of the problems that Borel has to deal, especially with non-uniform case, don't appear at all because the cocycle is from the beginning bounded. So you have this control here. So that part gets easier actually.
Right. The infinity is much simpler. Yeah. And what are the other applications besides this of this bounded cohomology, besides this stability question?
So I would say there's surprisingly many applications that come only from the toy case that I mentioned of the quasi-homomorphisms, because you will just put this into competition with the fact that that many people have proved non-vanishing results for all kind of groups. So let's say, for instance, the mapping class groups typically have a huge second bounded cohomology, and so this vanishing will give you another proof of the fact that you won't have non-elementary representations of higher rank lattices into mapping class groups. So this sort of thing, and you can apply this to another type of application comes from the fact that bounded cohomology is well suited to anything that is measurable and ergodic theoretical. And so, for instance, you can use that to give restrictions on orbit equivalence problems in ergodic theory. So that'd be another class of applications.
Very interesting.
Thank you very much.
Yeah, you must be hungry for food.
We are late, but let me ask you a question. If you have G invariant functions, like if VG is not zero, so two questions: whether do you know what's the answer in this case, and for the trivial module, and can you combine the two? Namely, if you can you always just say that if you know what the answer for the trivial module, then together you know for a general module.
Right. So yes, I can answer the question. So yes, I know exactly what happens. Unfortunately, it will not make you super happy. So because what happens, so for let's, instead of saying, you know, when this is not zero, right? Let's just first reduce to the case where you really have trivial action on the module, right? So then what happens is that then H2 bounded of G with coefficient in this is actually isomorphic to the ordinary cohomology, right? And we know that this is we know exactly what this is in ordinary cohomology. It's either 0 or V, and it is if and only if, so it's non-trivial if and only if G is a formation type. So let's take a simple group and then you go factor by factor. Okay, so the good news is that we know the answer. The second good news is that what we cared about was the kernel of this map, of this comparison map. And so this tells you that the kernel is always trivial. So it means in general, so therefore in complete generality, the kernel, which seems to be what we care about, is always 0 without any assumption. The only reason, so I could say in that sense, we know exactly what happens. The reason this is not great for next talk is that combining the, well, I guess I'll let Bharat talk about this, but combining the case of invariant vectors with the case of, with the general case of non-invariant vectors is straightforward for bounded cohomology, but perhaps not in the setting that we'd like to study together. I don't know if that answers your question. But at least it made you disappear. So.
Yeah. Okay. Thank you very much. Are there any other questions?
I have a question. Yeah, thanks for the talk. So I just wondering if your method can be helped to compute some Kazhdan constants for some groups.
I know of I know no relation between the two problems. So I'm not aware of any. Yeah, to me it sounds like, yeah, maybe I'm just, you know.
I think that question should be asked to Marc Burger, since he worked with you and on the other one.
Okay, yeah, thanks.
Any more questions? Okay. If not, the local people can go to lunch. Thank you, Nicola, once again. And next week, Bharat will explain more about stability and asymptotic cohomology. It will be independent, but I think people who digested this one will find it easier to understand next week's talk. Thank you all and see you next week.
Thank you very much.